Okay, so this next question that I'm going to pose in front of you is going to connect you with the bias theorem. Although it may not appear like that, but uh, it is kind of, you will need the bias theorem to answer it. Maybe you may be able to solve it even without utilizing bias theorem. And today, in this pandemic era, this question is actually highly pertinent. We deal with it. Almost all of us may have to think about it, either for us or for our family members or someone we know, or etc. And so it's kind of relevant in today's world. So, okay. So I'll go to the question now. And by the way, this question I'm posing in front of you because it will help us answer this question of what constitutes information, what is the notion of influence that gets defined when we define information. Okay? So suppose that there is some prevalent disease. I have called it disease C. C stands for, you can guess what it stands for, but it's fine if you don't know what it stands for. So there is some prevalent disease C, and there is some test which is used to detect the disease. Okay. Now, suppose that in the general population, if you pick somebody at random, there is only 1% chance that that person has that disease C. So there is only a small probability that the person is infected. Now, suppose somebody goes and does the testing for C. What happens is the test is not perfect, and so there is a false positive rate of 5%, which means that even if you don't have the disease, you are going to get nervous and you are going to have perspiration and all that because this test wrongly told you that you have the disease, and the chances of that happening is 0.05. But the test is not worthless. It is actually pretty good. It tells you with 95% chance that you have the disease if you actually indeed carry the virus. Okay, so it has a correct positive rate of 0.95. So now this is the question that you take the test and the test result unfortunately comes out positive. Okay, so the question is, what is the probability that you actually have this disease? So again, I'm going to open this poll. And I'm going to ask you to answer this question. So you should start working on this.
Sir, can you repeat the last statement? We get positive, so what is the probability that we have or we do not have?
We have the disease. Okay, so that is the question. What is the probability that you have the disease if the test result is positive? So that is the question, and then you can answer your answer. You can add your answer here, and yeah, I'm going to give you maybe a few minutes to solve this question. Let us see how many of you actually can answer this question. Okay, it's going to be 2 minutes. In JEE, you wouldn't get this much time to answer such a question. Has anybody finished the problem?
Yes. Yes, sir.
Are you able to respond to the
Yes,
poll?
sir.
Are you
Yes,
able
sir.
Yes, sir.
Yes, sir.
I'm not able to see somehow your answers, but anyways, maybe I'll see it later. So I will close the poll. Okay, so actually, yeah, I do see. Okay, fine. So about 125 of you answered. I am not able to see your answers, but maybe I'll take a look at it later on. Okay, so those of you who answered correctly, let me see. Deep, yes, Deep has answered correctly. I can see Deep Shah has answered correctly. Anshu Suthar has answered correctly. Okay, so those two students I know have answered correctly. Maybe others have also. So yeah, okay, fine. If you knew how to solve this question, maybe this is going to be a little bit of a different, maybe slightly different way of thinking about it. If you don't know how to answer this question, then definitely this will be of help. So I'm going to let's see. Okay, maybe I'll just draw here. So I'm going to draw here. Let us see this one. Okay, so I'm going to say C. Okay. So sorry about that. Okay. So I'm going to say that if you don't have the disease, then I'll make this C equal to 0. And if you have the disease, I'm going to make C equal to 1. Right? So these are the two possibilities. You may have the disease, which is C equal to 0, and you may not have the disease, which is C equal to 0, and you may have the disease, which is this possibility that C is equal to 1. And then over here, I'm going to write another parameter called T, and T is equal to 0 means what? That you took the test and it came out negative. So that is what T equal to 0 means, right? And then the other possibility could be that you took the test and the test result came out positive. So T is equal to 1 in this case, right? So these are the various possibilities. Now, we will say that the good thing, the part where the test works perfectly is if you don't have the disease and you take the test result comes out negative. T is equal to 0. On the other hand, the test should tell you that you have the disease, so that if you actually have the disease and the test result comes out positive, then that is also good, right? And what this problem says is that both of this happen with, what this says is both of them happen with probability of 0.95. So this is the probability of both of them happening. Okay, and then the other possibility is that you may not have the disease, but it turns out that the test says that you have the disease. This is the wrong thing. And the other possibility is that although you have the disease, when you take the test, the result comes out negative. So this is also not good. And the probability of either of them happening is one minus p. Somehow this thing is giving me trouble today. But we just move on. This is 1 minus p, which is 0.05. Okay, it's not working very well, so I'll move on. But you get the idea that this is the way that you can visualize the problem. There is this disease status, which is denoted by c equal to 0 or c equal to 1. And then there is the test outcome, which is denoted by t equal to 0 or t equal to 1. Right? Now, what you will notice is that I can actually draw a line, in fact. I can draw a line somewhere right here. And I can say that what we have availability to is just this side of the line. All that we know is the outcome of the test, right? We don't know whether we actually have the disease C or not, because this is somewhere residing in our body. If we trust the test, then whenever it says 1, we will believe that we have the disease. Whenever it says 0, we will believe that we don't have the disease. But that is where the notion of belief comes into the picture. How much we believe in the test that we are taking, right? The test is actually a word here that I'm using. You may not actually need to go to a laboratory and actually conduct the test. Somebody may not stick the injection in you, collect your blood and do the actual test. The test is something that you can observe, something that you can feel. It's something that you have availability to. It could be just that the one day you wake up and you have a sore throat and you start coughing. And this happens a lot of times with my family members these days, that if that happens, they get worried that, oh, wow, maybe what if we have this coronavirus, right? So that also would be, I would call it t equal to 0 or t equal to 1. The mornings that we wake up and we are feeling fine, I would say that t equal to 0, and we happily believe that we don't have coronavirus. But who knows, even when we don't have any symptoms of coughing or sore throat, maybe C is still 1. And on the days when we wake up and our nose is running and we are coughing, T is equal to 1 for us, because our body is giving us an evidence. It is giving us an observation that something is wrong. But does it mean that C is equal to 1 because I'm feeling those symptoms? Well, most likely not, because there is a very good chance that C is equal to 0, and we are temporarily exhibiting those symptoms, right? So the message that I wish to convey is that this problem tells us that we have availability to just the observed effects or observed outcomes. And using the knowledge of what we have observed, we are always trying to update our beliefs, right? So that is where the belief also comes into play. We are trying to update our beliefs about the cause that underlies that observed effect. And so that is where the notion of influence comes into play. There is always some underlying cause which we can never access. We don't have connection, we don't have contact with that underlying cause. But that cause is what is influencing the outcome, t equal to 0 versus t equal to 1. So that is where, I said that information is connected to the notion of influence. So here we are saying that the cause, in this case, the status of the disease C, is influencing the observed outcome. And by looking at our observation, we are then kind of trying to work our way backward and update our beliefs regarding whether we have the disease or we don't have the disease. Okay, so that is the essence of what goes on with us all the time. And our brains are so much of experts in solving this problem that those of you who didn't answer this question or who struggled with the question or who answered wrongly, all the time you do this without your active awareness, right? Next time, if you start coughing and you feel an emotion of fear that, oh, what if I have coronavirus, right? That time you have already done this calculation inside your brain without your actual awareness. So, so that is why I was telling you that the definition of information is something that touches all of us all the time. And believe it or not, this problem that I just tried to show to you visually by drawing those circles and connecting those circles with arrows is going to help us a long way. It is going to help us a lot in answering these fundamental questions about what makes up the information. And this is where I'm going to try to motivate you about your potentiality. Okay, this is where I told you last time about Swami Vivekananda. About 75 years back, a mathematician called Claude Shannon. He was about 30 years old that time. He was working at Bell Labs in New Jersey. And he was thinking about very similar type of questions, that what is information, how to measure it, how to transmit the information, what will be the bottlenecks in transformation of information, etc. And actually, he was not even, his job was not even that. Okay, so he wasn't kind of actively thinking along those lines all the time. Okay, somebody said, what is the right answer? Yeah, so right answer is 16%. That is the right answer. Okay, and let me say. So 16% is the right answer. So if you got that 16% answer, you got it correct. So coming back to Claude Shannon, so he was working at Bell Labs. This was, I think, in late 1940s, and World War II was going on. And so American government had actually asked a lot of engineers to develop secrecy systems. You should be able to exchange messages across the Atlantic Ocean without the German army getting hold of it. And so you have to encrypt the messages, and it was all about finding ways of transferring information in an encrypted way. And so actually Shannon was working on that. And while working on that problem, he realized that he had to answer this question about what is the information. And so that is where he started thinking along the lines. And actually, he took a problem very much similar to this uh, disease C problem that I just asked you. And then he just pursued it. He didn't let it go. He kept thinking about that problem and what all that it told him. And, that is what was amazing about his work. His entire theoretical development that he came up with was his own thinking. He didn't leave his chair to come up with that theory. And you know, right, that Einstein also did something very similar. He came up with his theories of relativity while sitting at his desk in some patent office. And then they didn't have any computer or they didn't have any lab equipment. They didn't perform any physical experiment. Theirs was entirely thinking effort. So that is what people tell about Einstein's theories, and nowadays even about Shannon's theories, that to understand those theories, it is as if you are uh, in a thought paradise. Basically, all that you need is your brain and maybe pencil and paper. And what is really amazing about actually both of their papers, Shannon's paper and Einstein's paper, that it didn't require any concept beyond high school math. And still, because they did their work so thoroughly and they went to the bottom of the questions that they were trying to answer, uh, the output of their work ended up shattering the existing paradigm. They brought in a paradigm shift. And so that is what we will do, at least in the first few lectures of this course. We will try to understand what Shannon's intellectual thought process was. Okay, that is going to be our objective over next few lectures. But before we actually jump into that, let us just directly look at the final solution. It's, like you're reading a murder mystery. You like, those of you who like to read maybe Agatha Christie or Sherlock Holmes, this is going to be as if we are going to the last page of the novel and looking at the solution to the mystery. So this is the answer that Shannon developed in the year 1948, and that is what he published in that paper. And what is amazing is that this answer is still driving the design and the analysis and the research of today's communication system, 3G and 4G, and it also is influencing, and it is also kind of setting the baseline for the future communication systems, 5G, 6G, and it doesn't matter what generation it is. Even 100 years from now, people will still be tied by the theoretical developments that Shannon developed. And the analogy applies, right? Einstein said that nobody can cross the speed of light. So likewise, what Shannon said is some limit that no matter how smart or how capable a communication system designer is, he or she will never be able to violate the theoretical formulation that Shannon defined. So we are now going to look at what Shannon has proposed, or what Shannon has derived as the solution of his theory. And that is what actually you have already done in your last lab. So I'm going to very quickly go over some of the topics that you have dealt with in your lab that you did. So Shannon thought about the origin of information, generation of information, and the transfer of the information. And he said that if I want to crystallize, if I want to kind of remove all the unnecessary complication and go to the bottom of what actually makes up a communication system, then he said that this is what I would come up with. This is what I would draw. And actually some diagram like this is one of the first diagram that is in Shannon's 1948 paper. You can actually do an online search. And so what he said is that in order for an information transfer to happen, there has to be a set of messages, which I have drawn over here, right? So this is the set of, sorry. So there has to be a set of messages. And what the transmitter or the generator or the source of information does is that he or she selects one message out of this set. It selects one member of this set. And Shannon said that it is this aspect of selection which generates the information. He said that it almost doesn't matter what the set members are. I'll give you an example. This set could be the letters of English alphabet. And when you write a particular sentence, you are selecting one letter. You may start with D, so then you are selecting T, H, E, one after another. But anyways, you are selecting one letter out of a set which is comprised of 26 letters of an English alphabet. What Shannon realized is that the exact composition of this set doesn't matter. It doesn't matter whether this set is of English language or Gujarati language or Hindi language or Chinese or any other language. What actually constitutes the information, what generates the information is the act of selection. That somebody is selecting one particular member of this set. And today we can understand that, right? I mean, we have translators, even online translators, the machine intelligent translators. You can write it in English and they will convert it to Gujarati or vice versa. Or sometimes those AI translators don't work very well, but then you have human translators which can do the job for you, right? So, for example, when American president visits China, he speaks in English, but then there is a Chinese translator who will be translating what he is saying into Chinese language. So that was the message. That was the thought that Shannon defined. That yeah, you need a particular set, but the exact definition of the members of that set is not that crucial. What is actually important is the act of selection. And that is what generates the information. Few months back, you selected DAICT compared to some other colleges. And it is that selection which is important, which kind of consumed you. Before coming here, you were absorbed in that task of selecting. And that selection is what we do again all the time. Some of our selections are easy, but then sometimes you have to make some very momentous selections. And so Shannon said that selection process is the reason why information gets generated in the first place. But then after selection, that particular set member has to be transmitted. And for that, we need a communication transmitter. What the transmitter will do is it will take this message and it will convert it into a signal, a physical signal. This signal is what you would study in physics. This selected message is not actually any physical object. It is residing in our brains almost. But whereas the signal is something that is a physical entity. And the signal is what gets transmitted over the communication channel. And in that process, it might get corrupted by some additive impairments. And then the receiver gets that signal. Okay, so let me. Sorry, just bear with me. Okay, so the receiver gets this signal, may be corrupted with noise. And the task of the receiver is to convert the received signal back to the message. And hopefully at the receiver side, the person who is on the other side, maybe off the telephone line, he or she will end up selecting the same message that the transmitter has selected. And so if that happens, when the transmitter is able to influence the selection of the same message that the sender or the transmitter or the source has selected, then we say that information has been communicated accurately. Okay? So that is the block diagram that Shannon defined of any informative communication system. So you see what has happened is that transmitter has selected a message here, and then the entire role of this communication system is such that through that the receiver is influenced to select the same message that the transmitter has selected. And when that happens, we say that information transfer has been successfully achieved. So again, this notion of influence has entered the picture. But what will corrupt this influence is this noise. Because of the noise, what will happen is that the received signal will not be an exact version of what was transmitted. And so receiver may think that actually the transmitter has selected this message. Then basically what has happened is the noise flipped this arrow from where it should have been pointed, this actual correct member of the set. The noise made it flip to a wrong member of the set, and then we say that message has been unsuccessfully communicated. Okay, so that is what the overall concept of a communication system defined by Shannon was. Okay, so now we will go to your lab that you did and look at some of the parameters that you studied in that lab. So the size of the message set determines the number of bits that are required to convey the message. It is the logarithm base 2 of the number of messages. And then the other important part is how fast the messages are selected. So if the message size is large, so basically if M is large, and if the messages are getting selected by the transmitter very fast, then what happens is that the bit rate becomes fast also. Maybe in the lab we had RB instead of R. But what it means is the number of bits per second. So basically what Shannon said is that if the bit rate R is large, meaning you are trying to send a large number of bits per second across the communication channel, then the communication system has to do a lot more work compared to if bit rate R is small. And so what is meant by the work is the power that the receiver has to get, the bandwidth that the transmitter has to use to transmit that physical message, and the noise power. These are the parameters that the communication system has to work with. And then Shannon came up with this relationship that the bit rate can never be greater than the bandwidth times logarithm base 2 of this PS over Pn, which we have called SNR. And if you plot this formula, bandwidth W times log base 2 of 1 plus PS over Pn, if you plot it as a function of SNR here, then you get this this curve, which is probably one of the curves that you produced in your lab. And this is sort of like speed of light. Shannon said that you cannot cross this blue curve, meaning that you can never transfer information faster than what this blue curve says. So if you have, let us say, SNR of 20, you cannot be over here. This is not permitted. You cannot transmit bits like 5 bits per second for every hertz of bandwidth. That is not going to be possible, no matter what you do. But you can actually transmit bits as fast as 4 bits per second per hertz. And so that is where today's systems are working with. This is what the systems today are working with. 1G and 2G, they were operating somewhere over here. They will have signal to noise ratio as large as maybe 80, but they will be able to still transmit only 2 bits per second per hertz. So their data rate is pretty feeble, right? But as the communication technology has improved, maybe from this 2G point here, 3G came up to here. 4G came up to here. And then maybe 5G's goal is to be somewhere over here. So this is what the communication system today are trying to do. Come as close to the blue line as possible. Maybe in the future, there'll be a communication system which touches the blue line. And then that would be the ultimate performance. What this equation also says is that there are two important concepts. One is the concept of bandwidth efficiency, which is the ratio bitrate divided by the bandwidth. And it is obviously very good if you can have this ratio R divided W as large as possible, because what it means is that over a limited amount of bandwidth, you can transmit more and more number of bits per second. So it is obviously good to make this eta B, this energy efficiency, as large as possible, right? So you have to purchase small amount of bandwidth, and bandwidth is very expensive to purchase, by the way. So you can have a limited bandwidth, but you can still satisfy the users if they're watching movies on Netflix or YouTube. Their movies will download pretty fast. So having a large value of bandwidth efficiency is very useful. But the problem is that in addition to having a large bandwidth efficiency, the designer of a communication system also wants to minimize something called energy efficiency. And the energy efficiency ultimately is nothing but how much power or how much energy you need to be able to transfer the information. And if you end up asking a lot of power to be able to transmit certain video or certain file, then that is also not good, because your phone will be dead. Its battery will die. So you want to be using the energy that the battery provides in a very efficient manner, and that is another important metric. And what Shannon showed by that equation is that it is most of the time it is hard to get best of both. So you can either increase bandwidth efficiency, but then you will have to live with a reduced energy efficiency. Or if you want to increase or improve energy efficiency, then your bandwidth efficiency cannot be large. And one of the underlying kind of read between the line type of concept that was there in your lab one is that this trade-off between bandwidth efficiency and energy efficiency. You may have seen that if you try to increase one, the other goes down. And this can be also thought of as the trade-off between power and the bandwidth. Sometimes as an engineer, you may have only a fixed transmit power, meaning that your phone battery is of certain size and the antenna is of certain size. So basically the antenna cannot radiate more than some fixed amount of power. Now, given that limitation, suppose if you want to increase the data rate, then what Shannon pointed out is that you can do it if you are willing to increase the bandwidth. On the other hand, if you have fixed amount of bandwidth, and if you want to transmit more and more number of bits per second, then you can throw more power at it and you may be able to get that particular bit rate. Okay, so that is one very high level summary of the lab that you did yesterday. Let us see how much time we have. Okay, we have 10 more minutes, so maybe I will be able to complete the rest of the slides. Okay, so now, see, I was first talking about why you should be interested in this subject. And I gave you some conceptual reasons. You know, I told you that this course is probably one of the few courses that asks you to think about some very fundamental questions. And if you fully understand the answers to those questions, then it gives you a level of satisfaction that is sometimes not available in some other study topics. The other reason why this course is quite nice is that this is more of a practical reason, that in this course we will kind of do a sampling of many different subjects. Okay, so first and foremost, right off the bat, we will be talking about information theory. This is the theoretical development that Claude Shannon did. So we will be understanding a part of information theory. Information theory is a very deep subject, so we won't be able to cover much of it, but at least we'll get some sampling of it. And in the process, information theory, by the way, is very intimately tied to another subject called coding theory. It's also a fascinating subject, and we will kind of get a preview of coding theory as well. And in order for us to understand information theory, we will have to first actually study some concepts of probability theory. Maybe this bias theorem is the very first topic that we will take up. And in that connection, we will get our arms around some of the basic concepts of probability theory. And this bias theorem is actually lies at the heart of this estimation and detection theory, which is, by the way, connected to machine learning. So this is another topic that we will be kind of studying to some extent. Later on, we will be actually getting into some of the topics of signal and systems. Okay, so this one is not working. My pen is not working. So let's see if I can write it. Signals and systems. So we'll be working with some of the topics of signals and systems here in this course. Okay. And then obviously we will be studying analog and digital communications as a part of this CT111. So that is what CT111 is going to be all about. Some of these topics we will be spending more time on, some of them we'll be covering just the basics of it. But this course will expose you to all these multiple different domains. So that is, I would say, why you should be interested. That question is also kind of answered here. Okay, and then the other part of why you should be interested in this course is that is where a lot of the action is these days in terms of communication industry, in terms of even machine learning community. There's a lot of work that is happening in moving our entire human society from the 4G wireless to 5G wireless. And this course is kind of going to expose you to what are the type of engineering advances that need to happen so that the cool things of 5G can be made reality. And so before we get into that, I want to mention that, you know, as an ICT engineer, your goal, and actually you are well placed to achieve that goal, is to differentiate yourself. That differentiation is like an all important thing, right? In the medical domain, if you are an MBBS versus if you are a neurosurgeon, right? Obviously, neurosurgeon will be very much I wouldn't say in demand, but his expertise will be valued a lot because what neurosurgeon can do, an MBBS cannot do. And if somebody is having some neurological problem and his life is at stake, and if a neurosurgeon comes along and solves that medical problem for him or her, then the value of that neurosurgeon will be really felt by this patient, right? The reason is because he or she is able to do something which the other doctors are not able to do. That is the differentiation that this CT111 also can potentially give to you. Because here you will be studying the concepts and you will be studying the topics which will differentiate you from maybe a computer science student. Although you will also be studying subjects of computer science, this ICT degree is unique and it is greatly beneficial to you in the way that you will have some skill set, you will have some knowledge, some expertise that those who are just getting a CS degree won't have. And to put it bluntly, very starkly, you can actually become rich, right? Just the way a neurosurgeon is likely to be much richer than an MBBS. And so the reason I'm saying that forcefully is because it is that as a neurosurgeon, you are very much going to be in demand. The reason is because there is a lot of attention and a lot of focus in developing 5G systems. And there is a great ambition that people, industrialists and engineers and mathematicians and researchers all over the world have put together. This is their vision, okay? This slide shows the vision of what the 5G should be. You can do a search on this 5G white paper by Next Generation Mobile Network Alliance. And what they have said is that 5G should provide broadband access in dense areas. So people should be able to watch videos on their phone as if they are watching videos on their cable TV. The quality of the video and the download speed of the video should be as fast as cable connection. Broadband access everywhere, meaning that you can be in some remote village and you still should be get a very high data rate, 50 megabits per second. High user mobility, you may be able to get a very high data rate connectivity even if you are in a bullet train. There's something called sensor networks, which are considered to be a path-breaking technology. But in order for that Internet of Things to work, you need an underlying communication network. Extreme real-time communication or tactile internet, basically touch-based internet. Lifeline communication. So if there's some natural disaster, we need to set up a communication system in those scenarios. Ultra reliable communication where some surgeon may be able to perform surgery remotely through using some robot, etc. So these are some of these services that are being planned for 5G. This is what I already mentioned to you, so I won't spend too much time on this. This is kind of another way to represent the vision of 5G system. And you can get this from this ITUR document. What this vision is that there are going to be a triangular type of objective with 3 vertices. One is called enhanced mobile broadband. This is what I already mentioned to you, that you should be able to get a very large data rate, maybe even as much as gigabytes per second on your cell phone. And so using that, you should be able to do 3D video, and you should be able to get ultra high definition videos on your screens. And then there is something called massive machine type communication. So that is what I was telling you, the sensor networks and the Internet of Things, which, for example, can build up a smart city or a smart hospital or a smart home. And then there is the third vertex, which is called ultra reliable and low latency communication, URLLC. And so here is where the self-driving cars come into play, and some of these mission critical applications, industrial automations, those are covered under this URLLC domain. And so for all of this to be realized, what is needed? You will see a lot of these words: gigabytes in second, low latency, ultra reliability. These are the topics that we are going to be studying in this course. We have already studied this bits per second topic. And then this is the last slide for today, which shows where the world is today in terms of 3G and 4G. So this yellow colored bars are where the technology is today, and the blue is where the target is. So peak data rate in gigabits per second, the target is to increase it by 24, right? You will see here this spectral efficiency. This is what you have already studied in your lab 1 and what we just recently talked about. This is coming from ITU, okay, International Telecommunication Union. This union is made up of some very experienced engineers, scientists, mathematicians, industrialists. This is their career. This is what they do day in, day out. And it is this is the second lecture, and we are able to understand what the spectral efficiency is. And you have already kind of gotten your hands dirty with the notion of spectral efficiency, then the requirement of getting certain number of bits per second and so on. They also talk about energy efficiency over here. They want to improve the energy efficiency also by more than a factor of 10. Energy efficiency is also something that we have studied. And so this is the vision. This is where the industry wants to be, going from the yellow to the blue. And how to get us there? Nobody knows actually. This is the bleeding edge of the cutting edge, so to speak. So that actually brings me back to one thing that I had told you last time, which is that just like Shannon and Einstein, who took something very basic and they ran with it, keep your objective that you will come up with some really nice idea that the industry, and specifically this IEEE body, will accept. And they will give you credit for that. Okay, this is going to help us advance the technology and help us in attainment of the goals of the 5G that I just presented in that last slide. So today, at the closing, what I will impress upon you is that there is a way to study this course And there is a way to not study this course. I mean, for any course that applies, but especially for this course, if you take it as your run-of-the-mill course, if you take it as a vanilla subject that you have to take to fulfill your credit requirement for the second semester, maybe you won't get much mileage out of this. Okay, so that is one way to take it. Your life is going to be easy over next 3 months, and you're going to be happy. I'm going to be happy, but uh, I wouldn't recommend that way of taking this course. The way to take this course is to be ambitious and to say that yes, I really want to get a great mileage out of it. And if you do that, if you end up actually if you end up coming up with an idea which will take the whole industry and the academic research from that yellow bar towards that blue bar, right? At the end of this course, or maybe by the end of the year, if you come up with some smart idea like that, it's going to change your life. Okay, your life is going to get transformed. You will, by the time you do that, you will be so much kind of, you will be wedded with this topic of communication theory. And it's as if a bug has bitten you. It's like you have become addicted with this subject. And then the subject won't leave you. You will be thinking about it pretty much, I think, for the rest of your life. That would be a transformative experience for you, and that should be your goal. That is the way that I hope that you um, take this particular course CT111 over next 3 to 3.5 months or so. You may or may not be able to achieve that goal, but keep that as your high-level objective. Okay, so with that, I will stop here, and I'll
Hello,
see you
sir.
again Tuesday morning. I'm sorry, Thursday morning.
Sir, I have a question.
Yes, yeah, go ahead.
Sir, you said that in communication we we don't have ability to cross the graph that Shannon gave, right?
Yes.
Sir, in practical way, I totally agree. But sir, in theoretical way, I read somewhere that in quantum entanglement, where two particles are coupled, they means react instantaneously, no matter where they, what is the distance between two. So I think in theoretically at least it is possible to cross that graph.
Okay, I will suggest you to not go there. Okay, uh, that will be like a moonshot, or maybe not even a moonshot. It will be sunshot. It more or less you want to remain within non-quantum engineering. Quantum physics is going to uh, lead you far off the mainstream. Maybe later in this 4 years, if you take a course on quantum physics and then you want to apply quantum physics to information theory and communication theory, uh, then that is something that you can look at. But in this course, we are not going to be studying quantum theory, and quantum theory is not something that you can really make a mark on by having just the high school level understanding of the physics. So I would say probably that if you keep your ambition towards quantum physics and you say that by using quantum physics, I'm going to improve upon the Shannon's theoretical formula, then I am thinking that you're probably having an ambition which is maybe too large. I don't want to discourage you. I would say that you keep that ambition with you, but you pursue that goal after you study quantum physics, maybe not now. Okay, does that answer your question?
Hello,
But
sir.
uh, I am not going to defeat that theory, but I want to ask that in at least theory, Is it possible to go beyond this limit? I just wanted to ask that.
Uh, you mean by using quantum physics, can we violate this limit? That is what you're saying?
Yes. Yes, sir.
I don't know. I mean, I don't understand I mean, there is a field called quantum information theory. Uh, it's considered today to be part of information theory, but it's a subset of information theory, which is called quantum information theory. I do not understand quantum information theory actually, and so I don't have uh, expertise or knowledge to be able to answer your question. But what I will say is that Shannon defined his problem by making certain assumptions, and if you say that those assumptions are satisfied, then there is no way that you can bypass that Shannon limit. So what his assumptions are and whether they are realistic or not, that is something that we'll be studying in this course. But the general understanding, the broad acceptance in the research community, in the academics, in the industry is that Shannon's formula, which you implemented in the lab, is like equal to mc squared. You can't violate it, or it's rather more like speed of light. You can't have a speed which exceeds the speed of light. And there are some extremely smart mathematicians and engineers who have spent 20, 30 years of their career thinking about this equation that you have programmed in lab 1. And nobody has been able to come up with a way of violating that so far. Okay, there was
Okay,
some
sir.
other.
Thank you.
Hello, sir.
Yeah, go ahead.
Sir, is this the rumor or reality that other countries have developed 5G?
Whether it is rumor or reality, how does it affect you?
Um, I was just asking.
Yeah. Um, uh, I am not a social scientist who studies which societies have developed which technology and so on. So I actually, again, I would say I don't know the answer to your question. Uh, but what I would say is that 4G versus 5G, it is not like day versus night or uh, black versus white. Uh, the 4G technology itself has various grades to it. The 4G technology, which was there five years ago, is not 4G technology which is there now. Because within 4G also there is constant enhancements and improvements. And similarly, 5G that will actually materialize in its initial days will seem a lot like 4G. But as the years progress, 5G will start becoming better and better. And at some point, you will say that, okay, now we are able to get some services which were not at all possible in 4G. So the answer to your question is that not only some specific countries, but all over the world where 4G has matured enough, uh, it in some sense is already becoming like 5G. Uh, Basically, it is like, if you have a car uh, and the car is getting old, so you start replacing maybe first the carburetor and then maybe compressor and so on, one after another. And then you start putting in more and more such mechanical parts. And now because you are doing those installations maybe 10 years after you first purchase the car, uh, it's going to work much better. Eventually, if you keep on doing that, you will end up replacing the engine also, and then the car will become as if it's like brand new latest technology car. In between, it is both 4G as well as 5G. So it is not, as I said, black versus white, but there's going to be a gray belt in between when the entire technology migrates from being called 4G to being called 5G. And I would say right now, even in India, we are in that gray belt. Okay?
Thank you, sir. Okay.
Yeah. Anyone else? Okay, so very briefly, how did your lab go last week? I mean, sorry, last lab go yesterday?
Yes, sir.
Yes,
In
sir.
lab, there is a equation C is equal to B log 1 plus PS by PN. Then we have used
That is
PN.
that is the equation that we were just looking at. It is not only in the lab, right? In today's lecture, we had the exact same equation, if you notice.
So we have used B instead of PN. So why?
Sorry, what's the question?
Means P.
Sir, while solving the other questions, we took the assumption that our PN is equal to B, as our TA suggested us that we are supposed to consider that. So why is that we are confused with that?
I'm not able to understand your question. PN is supposed to what?
Sir, Pn is equal to n naught into b. That given
Yeah,
to
yeah. Oh, okay, okay, okay. PN is the power of noise, and I will not be able to answer that question right away because we will need some concepts from Fourier transformation and on that we'll be studying later on. But you think of this as a rectangular box, okay? Uh, the the horizontal axis or the horizontal dimension of that box is called the frequency, right? So if I want to draw this diagram in an XY plane, my x-axis is frequency, and my y-axis is what is known as power spectral density. What is power spectral density? We will not be talking about it now, but just take it like that. But x-axis is frequency, which you know, and this box has a width equal to the bandwidth. And bandwidth is a frequency domain concept, so it matches. So if you visualize in your mind this type of a box, a rectangle, whose horizontal dimension is b, and the vertical along the y-axis, its height, which is this power spectral density, is given as n naught. Then what the mathematics shows is that the power of the noise, what we have called P of n, is given as the area of the box. So now, what will be the area? It will be obviously the length times the height, or the length. If you imagine this rectangular to be vertically oriented, the height is n naught. This is the power spectral density of the noise, and the width is equal to the bandwidth. So the noise power is going to be n naught times b. Okay. So in order to understand what is power spectral density, why the noise power is equal to the area of that rectangle, we will need to understand some concepts of Fourier transformation at the least. I don't know whether we'll be having time to do that now, but if you study that topic now, I'm sure you will understand it later on, maybe in some of the courses that you will take later in your degree program. Okay, any other question? Okay, if not, then I will end today's session, and I'll see you
Uploading these slides in Google Classroom.
on Thursday at 8:30. Yeah, sure. I'll be posting this slide on Google Classroom. I had some difficulty with this pen tablet today. So maybe the annotated slides with the markup, I don't know if I'll be posting that or something else. But yes, I'll definitely be putting the slides on. I mean, I'll be posting that slide on Google Classroom. Okay, so see you then. If you have not completed Lab 1 yet, as you know, you have time till this Sunday or next 5 to 6 days to work on it. But finish it by Sundays so that next Monday there will be a new lab assignment. And the content of that lab we will be talking about, we'll be studying that concept, which is mostly going to be this probability theory and Bayesian mathematics. So we'll be covering that on Thursday when we meet. Okay, so see you. Bye.
Thank you, sir.